Sorry, Dr. Memari, one more time. The experiment is calorimetry. We are going to determine heat of reaction, heat of making solution, and also determining a specific heat of a metal using the concept of the calorimetry, or the amount of the heat that is being gained or lost. Using the equation, we are trying to find the specific heat for a metal. First part of the experiment, we are using a styrofoam cup as the calorimeter. Usually one, just to be safe, I'm using like two, one in the one inside another one. I'm using this as a simple calorimeter. Because it's light weighted, I support it with a beaker. So when I'm using the thermometer to measure the temperature, it doesn't trip and it doesn't spill. So we have first step, we are going to, for first part of the experiment, we are going to measure 2 grams of solid sodium hydroxide as fast as possible, because in last experiment, I said sodium hydroxide is not a stable compound. It will gain water, it would absorb water from the environment. So I'm going to measure 2 grams. And since it comes in the form of the small pellets, it's very hard to get exactly 2 grams. But for our experiment purpose, as if we get very close to 2 grams, but we record exact mass that we are measuring, it would serve the purpose for the experiment. So all we need is the exact mass. The amount is going to be about 2 grams. So please record the mass of the sodium hydroxide measured as 1.973 grams. That's the mass of the sodium hydroxide measured in the styrofoam cup as being used as the calorimeter. We are going to measure how much heat is going to be released when the sodium hydroxide forms a solution or is dissolved basically in water. We use a digital thermometer, and we measure the temperature to first decimal place. So I turn on the digital thermometer, place the probe inside the water. Want to compare the temperature of the water before mixing and the temperature of the water after we mix with sodium hydroxide. So I'm going to hold it for about 30 seconds to stabilize the temperature. I want you to record this temperature as the temperature of the water itself. And that number, it's very clear. So I don't want to read it wrong, because now I'm not actually seeing it. Okay, what is the temperature? 22.8. Okay, so we have that number. Next, we are going to add the 100 milliliters of the deionized water from the graduate cylinder that was measured and into the sodium hydroxide, solid sodium hydroxide, and we are going to stir using the thermometer probe as the stirring rod, also using like for both purposes. And we wait until the sodium hydroxide is completely dissolved. Also, the temperature on the thermometer is going to stabilize. So when the solution is, at the beginning, the solution is completely formed. So all the sodium hydroxide is dissolved. The temperature is going to increase because temperature is released in this reaction, is an exothermic process of the reaction. At one point, the temperature would reach to maximum temperature. That's the point that all of the heat or the reaction is complete. And if we continue measuring, the temperature is going to eventually drop. And at that point, what it means that there is no chemical reaction, but the calorimeter that we are using, of course, is not the perfect calorimeter, is not insulated, especially with the open lid here, it would lose some of the heat to surrounding. So we would record the maximum temperature. Because the solubility of sodium hydroxide Of course, it's solid and it comes in a small pellets. It takes time. We just have to be patient here. And as soon as the temperature starts dropping, I'm going to monitor it and I get the maximum temperature and I will show you. So I would continue. So I wait for the maximum temperature. Basically, I have to wait until the temperature starts dropping. .0 was the highest temperature that I saw so far. And I'm going to look with the same at the same time you're looking at 29.0. And if it doesn't go higher than that, that's what temperature you are going to record. Okay, that's the first part of the experiment, 29.0. Okay, for the second part of the calorimetry experiment, we have 50 milliliters of HCl. I'm going to use the graduate cylinders. The graduate cylinders, they were washed and dried prior to experiment. So I have my HCl measured in 1 graduate cylinders, about 50 milliliters. I like to make it as close as possible to 50, and then the last drops adjusted with the dropper, so I don't have to go kind of back and forth. 50 milliliter of the solution of HCl in 1 graduate cylinder, and 50 milliliters of sodium hydroxide, 1 molar sodium hydroxide in another solution. Meniscus should touch the 50 milliliter line. So I get as close as possible to 50, adjust the last drops using dropper, make sure that the meniscus is at 50 line, exactly. We want the temperature for the HCl. So we record the temperature for the HCl. I try not to give all the numbers to you, so I want you to record the temperature for HCl. The temperature for HCl. Okay, perfect. And I'm going to wash it, so I'm not bringing any acid to the base, because if there is a reaction, it can increase the temperature. I want just initial temperature for the sodium hydroxide. Initial temperature for sodium hydroxide solution. Record the temperature for initial temperature for sodium hydroxide. If you take the average of these 2 temperatures, that will give you the initial temperature of the mixture. So we are going to transfer the sodium hydroxide into the calorimeter and followed by transferring HCl into the calorimeter, and we measure the temperature. This is a neutralization reaction, exothermic reaction. The temperature is going to increase. We are going to record the maximum temperature again. So I want you to monitor the temperature. look for the maximum temperature. So record the temperature as the final temperature or temperature after mixing. Okay, record this temperature as the highest temperature or the maximum temperature. Okay. That's the maximum temperature and has not moved, is not increasing. So this is the temperature that you need for your calculation for part 2, solution of NaOH and HCl. Okay, the temperature is dropping, so I don't have to hold it anymore. We can stop the recording. Okay. You also need measuring the heat that is released when solid sodium hydroxide is going to react with the HCl. So basically, beside the part that is calorimetry, measuring the temperature in this experiment, you are also going to apply the Hess's law and make sure that the amount of the heat that is released by solution plus the heat of the neutralization, it equals to the amount of the heat released from this last piece, which is using sodium hydroxide, solid sodium hydroxide, plus a solution of HCl. Because what is happening here, at the same time, sodium hydroxide is being dissolved in water because HCl is an aqueous solution, is 1 molar, so mainly is water. Sodium hydroxide will be measured. Did we record the mass for this? The mass for the sodium hydroxide, exact mass needs to be recorded, and that is 1.959 grams, about 2 grams, but you need the exact mass of the sodium hydroxide. We are going to measure 100 milliliter of the HCl. And 100 milliliter, I get as close as possible to the 100 milliliter and I adjust the last drops. That's the fastest way or easiest way for me to adjust exactly at 100. The meniscus should go to 100 or align with the 100. Okay. So I have the 100 milliliter. I measure the temperature of this solution of HCl in the graduate cylinder as initial temperature, which is the temperature before mixing. So record this number, change the angle so you could see it better. Record this number when it's stabilized, record it as initial temperature for before mixing or HCl, temperature of the HCl. Okay, that's the temperature. It is stable. Record that number, please. Perfect. Now we are going to mix the HCl. We are going to mix the HCl with the sodium hydroxide. And record the maximum temperature that this reaction mixture reaches. I'm going to stir it, and the temperature is increasing. The temperature is increasing. I just have to wait until all of the sodium hydroxide is dissolved, and I will adjust the angle for you to see it better. But right now, I'm still waiting for sodium hydroxide to dissolve and react with HCl. So two things is happening at the same time. Sodium hydroxide is dissolving, sodium hydroxide is reacting. It does make sense if more heat is released, but we want to see that on the experiment by measuring the actual temperature after mixing. So we are looking for the maximum temperature. Maximum temperature is not stabilized. I mean, I could see the maximum temperature has reached, but is not stabilized. I want to make sure that it is stabilized. Okay. Now, this is the highest temperature that we have, a stabilized temperature. You record this number of 35.5, that was the maximum temperature, is dropping, so it's okay. 35.5, that is the temperature. Ideally, the temperature or the amount of the heat that is released from solution, which was the first part, solid sodium hydroxide plus the water, if you add that to the heat released from neutralization reaction, when we had the liquid or aqueous solution of HCl plus the aqueous solution of sodium hydroxide, if you add those two together, it should be equal, in theory, to the amount of the heat that is released from this reaction, which is solid sodium hydroxide with aqueous solution of HCl. If you see the numbers are not matching 100%, you can explain that by factors that could affect. One of the factors that could affect is that the sodium hydroxide that we have, the 1 molar, is not standardized. It was made and it was labeled as 1 molar sodium hydroxide. I did not standardize to make sure that it is 1 molar. I'm explaining this to you so you could see or understand the difference from the theoretical to the experimental value, and you can use that in explanation part of the experiment as well. So we are done with the heat of the solution and neutralization. Next part would be the specific heat for metal. Okay. For the next experiment, sorry. Okay. Next part of the experiment, which is determining a specific heat of the metal, we are going to use the fact that if we mix hot metal with cold water, hot metal would hot metal would lose heat and cold water would gain heat. The amount of the heat being transferred is equal. Since we have the information for mass of the water, we have to get the mass of the copper. We have initial temperature for cold water. We have specific heat for water. And experimentally, we will find the final temperature for water and for copper. Initial temperature for copper. And then we do the calculation to find the specific heat for metal. One of the steps of the procedure asks for the measuring of the mass of the test tube, empty test tube. So I can't leave the test tube flat on the scale. So what I'm going to do, I'm going to leave a beaker, tear the beaker, the mass of the beaker, and now I'm measuring the mass for test tube by itself. If you can record this mass as the mass of the test tube by itself, Then I transfer some copper shots into the test tube. The amount of how much it's going to be, it depends on how much hot water I have, what's the level of the hot water. But I don't like to make it too heavy because then it would slide from the test tube holder. So we measure, but we have to measure the exact mass of how much copper is used. Please find the mass of the copper plus the test tube, and then you would find that by subtraction, the mass of the copper itself. Now, we are going to place the copper using a test tube holder. I'm going to place it in a hot water bath and let it stay for about 10 minutes. And within the 10 minutes, the temperature of the copper is going to be equal to temperature of the water. So we have it there for 10 minutes. While we are waiting for that, we can while we are waiting for the temperature of the copper to go up to reach the temperature of the hot water, we are going to prepare for the rest of the experiment. We need the calorimeter, which is a homemade or house recipe for calorimeter, to a styrofoam cup secured in a beaker. We measure 100 milliliter of cold water. That's the temperature of, and we measure the temperature of the cold water. This is the temperature or initial temperature for water, and I would use 1 decimal place for it and measure the temperature. I can pour it into a styrofoam cup and measure it in the styrofoam cup. So I will have the temperature. I always wait after using the thermometer, I always wait for the temperature to stabilize. And when we have a stable temperature, I want you to record that number. Okay, record this number as the initial temperature of cold water or initial temperature for water. Okay, 23.6. And after the 10 minutes is up for the heating up the copper, we measure the temperature of the boiling water also. The temperature of the boiling water is going to be used as initial temperature of copper. Initial temperature for copper. Okay, that's 101.5. It fluctuates, so I want you just record the 101.5 for initial temperature of copper. This is for the hot copper. Okay, it's been 10 minutes already, and we measure the temperature of the boiling water as initial temperature for copper. And I'm going to transfer, by the way, into the cold water of the hot copper into cold water and look for the change in temperature of the water. Heat is going to be transferred from hot metal to cold water, and the temperature of the cold water is going to increase. I'm again looking for, sorry, I have to turn off the gas. I'm looking again for the maximum temperature. And when the temperature starts dropping, or if it stays stable, I would record the temperature as the temperature of, as the final temperature. So this temperature is is stabilized now. Okay, the temperature is stabilized, just moving between the 27.7, 9, and 8. So see if it stays, if it's stabilized, we record this number. Okay, it moved up, so we have to wait. Okay, as soon as I try to tell you to record it, it just moves up again. So we have to give time. Temperature needs to be stabilized. Okay, 28.5. Record this number as the final temperature for water. And this is also final temperature for copper. The copper has lost heat, water has gained heat, and you are recording the same number for both final temperature for water and for copper, 28.5. Now that you have the final temperature for water, final temperature for copper, you have initial temperature for water and copper, you have the mass for copper, you have the mass for water, you have a specific heat for water, 1 calorie per gram per degree Celsius, or 4.18 joules per gram per degree Celsius. The only unknown in that equation is going to be a specific heat for metal, which we can find and refer to the lab manual, refer to the pre-lab discussions for this experiment to see how you do the calculation. Thank you.